In the vast expanse of the cosmos, there exists a star so bizarre, so utterly perplexing, that it defies everything we thought we knew about the laws of physics. This isn't science fiction, it's real, and it's just one of countless cosmic enigmas waiting to be unraveled. The universe is a treasure trove of mysteries, each one challenging the very foundations of astronomy and forcing us to rethink what we believe is possible. From stars that shouldn't exist to galaxies behaving in ways that leave scientists scratching their heads, the cosmos is brimming with phenomena that push the boundaries of our understanding. Today, we're diving into 32 of the most mind-bending stellar mysteries ever discovered, phenomena that don't just defy explanation, but also reshape the way we see the universe. These aren't just random oddities, they're cosmic puzzles that could hold the key to unlocking secrets about the nature of space, time, and reality itself. As we explore these awe-inspiring discoveries, you'll see how they've revolutionized scientific theories and sparked endless curiosity about the infinite wonders beyond our world. So, what if everything we've learned about the universe is just the beginning? What if the most astonishing truths are still hidden, waiting to be uncovered? Join us as we embark on a journey through the most baffling and breathtaking mysteries of the cosmos, and prepare to have your perception of the universe turned upside down. Deep within the cosmic void, there lies something so massive, so mysterious, that it's pulling entire galaxies toward it like a cosmic puppeteer. Known as the Great Attractor, this gravitational anomaly has baffled scientists for decades. Imagine a force so powerful that it can tug on galaxies millions of light years away, bending their paths and reshaping the very fabric of the universe. But here's the twist: we can't see it. Hidden behind the dense star clouds of the Milky Way's galactic plane, the Great Attractor remains shrouded in mystery, teasing us with its invisible influence. What makes this phenomenon even more perplexing is how it challenges our understanding of dark matter and the universe's large-scale structure. Astrophysicists believe the Great Attractor is part of a much larger cosmic web, a sprawling network of galaxies and dark matter that dictates the flow of the cosmos. Yet, its immense gravitational pull suggests there's something more at play, something we haven't fully grasped. As one leading astrophysicist put it, the Great Attractor is a reminder that the universe still holds secrets we're only beginning to uncover. Studying this enigmatic force is no easy task. Its location behind the Milky Way's galactic plane means that much of its light is obscured by dust and stars, leaving astronomers to piece together clues using indirect methods like radio waves and infrared observations. Despite these challenges, researchers have made significant strides, uncovering nearby galaxy clusters and superclusters that may be part of its gravitational influence. But the Great Attractor's true nature remains elusive, a cosmic puzzle that continues to captivate and confound. As we grapple with the mysteries of the Great Attractor, another gravitational enigma emerges: dark flow, a phenomenon suggesting that entire clusters of galaxies are being pulled towards something even more distant and unseen. But that's a story for another moment. For now, the Great Attractor stands as a testament to the universe's ability to surprise us, reminding us that even in the vastness of space, there are forces at work we're only beginning to understand. And as we peel back the layers of this cosmic mystery, one thing becomes clear: the universe is far stranger and far more wondrous than we ever imagined. While the Great Attractor tugs on galaxies with a force we can't fully explain, there's an even more bewildering phenomenon at play: dark flow. Picture this: clusters of galaxies, millions of light years apart, are all moving in the same direction at astonishing speeds. It's as if an invisible hand is guiding them, but here's the catch: this movement doesn't align with the universe's expected expansion. Instead, it suggests something far more profound, a force beyond our current understanding, possibly even beyond our universe. Dark flow was first detected in 2008 when astronomers analyzed the motion of galaxy clusters using the cosmic microwave background radiation, the faint afterglow of the Big Bang. They noticed these clusters were streaming toward a specific region of space at speeds of up to 1,000 kilometers per second. This wasn't just a random drift, it was a coordinated movement, almost as if they were being pulled by something colossal and unseen. But what could it be? One leading theory proposes that dark flow might be evidence of other universes beyond our own, exerting a gravitational influence we can't directly observe. Imagine that our cosmos, influenced by something entirely outside it. This idea has sparked heated debates among scientists. Some argue that dark flow could be a sign of large-scale structures in our universe, like superclusters or vast concentrations of dark matter, while others suggest it might hint at the existence of a multiverse. The very notion challenges our understanding of cosmology, raising questions about what lies beyond the observable universe. As one researcher put it, dark flow is like a cosmic whisper, hinting at something monumental just beyond our reach. Observational data has only deepened the mystery. Studies using the Planck satellite and other advanced instruments have confirmed the phenomenon, but they've also revealed just how little we know about its cause. The sheer scale of dark flow suggests it's not a local effect, but something far more significant, a cosmic puzzle that could redefine our understanding of reality. Yet, despite the tantalizing clues, dark flow remains one of the most elusive mysteries in modern astronomy. As we ponder the implications of dark flow, another cosmic enigma comes into focus: the vast, empty regions of space known as cosmic voids. These immense, dark expanses, devoid of galaxies and stars, play a crucial role in shaping the universe's large-scale structure. But how do they fit into the grand tapestry of the cosmos? That's a question we'll explore next, as we continue to unravel the mysteries that challenge our understanding of the universe. For now, dark flow stands as a reminder that the cosmos is full of surprises, urging us to look beyond what we know and embrace the unknown. Imagine a region of space so vast and empty that it defies logic, a cosmic desert stretching over 300 million light-years, where galaxies are almost entirely absent. This is the Boötes Void, one of the largest known voids in the universe, and it's as mysterious as it is immense. Named after the constellation in which it lies, this void is not just a gap in the stars. It's a profound enigma that challenges our understanding of how galaxies form and distribute across the cosmos. To put its scale into perspective, if the Milky Way were placed at one edge of the Boötes Void, the next galaxy would be so far away that it would take light millions of years to reach it. It's a place where the universe seems to have skipped a step, leaving behind a haunting emptiness. What makes the Boötes Void so puzzling is its sheer size and the stark contrast it presents to the rest of the universe. In most regions of space, galaxies cluster together like cities, connected by filaments of dark matter and gas. But here, the cosmic web appears to have unraveled. The void contains only a handful of galaxies, scattered like lonely outposts in an otherwise desolate expanse. This extreme underdensity raises questions about how such a structure could form. Did something prevent galaxies from forming here, or were they somehow removed? the answers could reshape our understanding of the universe's evolution. One intriguing theory suggests that the Boötes Void might be the result of an ancient collision between universes, a bubble of space left behind after a cosmic event so colossal that it pushed matter away, leaving this vast emptiness. Others speculate that advanced civilizations, far beyond our comprehension, might have harnessed the energy of entire galaxies, leaving behind this eerie void as evidence of their existence. While these ideas sound like science fiction, they highlight just how little we know about the forces that shape the cosmos. The Boötes Void forces us to confront the limits of our knowledge, reminding us that the universe is full of surprises. As we peer into this cosmic void, another mystery emerges: fast radio bursts, sudden and intense flashes of radio waves that last just milliseconds but release as much energy as the sun does in decades. These fleeting signals, originating from deep space, have puzzled astronomers since their discovery, but that's a story for another moment. For now, the Boötes Void stands as a testament to the universe's complexity, a reminder that even in the vastness of space, there are regions that defy explanation. It's a humbling thought, isn't it, that in a universe teeming with galaxies, stars, and planets, there are still places where the rules seem to bend, or perhaps where we're only beginning to understand them. Now, let's shift our gaze to one of the most fleeting and enigmatic events in the cosmos: fast radio bursts, or FRB. These are not your ordinary cosmic signals. Imagine a pulse of radio waves traveling across billions of light years, packing more energy in a single millisecond than the sun emits in decades. And just as quickly as they appear, they vanish, leaving behind a trail of questions and a scramble for answers. Fast radio bursts are like cosmic fireworks, brief, brilliant, and utterly mysterious. But what could possibly produce such an intense, short-lived burst of energy? That's the puzzle astronomers are racing to solve. The first FRB was detected in 2007, and since then, hundreds of these bursts have been recorded. Yet their origins remain shrouded in uncertainty. Some theories suggest they could be the result of cataclysmic events, like neutron stars colliding or black holes swallowing matter. Others propose more exotic explanations, such as highly advanced alien civilizations sending signals across the universe. While the latter might sound like science fiction, the truth is, we simply don't know. What we do know is that FRBs are incredibly challenging to study. They last for mere milliseconds, and their signals are often distorted by the time they reach Earth, making it difficult to pinpoint their exact sources. Recent discoveries, however, have added a new layer of intrigue to the mystery. In 2016, astronomers detected something unprecedented: a repeating FRB. Unlike the one-off bursts, this signal, named FRB 121102, repeated itself multiple times, offering scientists a rare opportunity to study its behavior. This discovery shattered the notion that all FRBs are singular, catastrophic events. Instead, it suggested that some might originate from environments that can produce these bursts repeatedly, like highly magnetized neutron stars known as magnetars. But even with this breakthrough, the full picture remains elusive. The implications of FRBs extend far beyond their mysterious origins. These bursts travel through vast stretches of the universe, passing through galaxies, gas clouds, and magnetic fields. By analyzing how their signals are distorted, scientists can map the distribution of matter in the cosmos, effectively turning FRBs into cosmic probes. They could help us uncover the missing matter in the universe, ordinary matter that's been hidden in the form of diffuse gas between galaxies. In a way, FRBs are not just mysteries to be solved, they're tools that could revolutionize our understanding of the universe's structure. As we grapple with the enigma of fast radio bursts, another transient phenomenon comes into focus: gamma-ray bursts, or GRB. These are even more energetic than FRBs, releasing in seconds the energy of billions of suns. But how do they compare to FRBs, and what do they tell us about the universe's most violent events? That's a story we'll explore next. For now, fast radio bursts remind us that the cosmos is full of surprises, offering glimpses into processes and forces we're only beginning to comprehend. They are, in every sense, a cosmic whisper, a fleeting signal from the depths of space, urging us to listen closely and uncover the secrets they hold. Gamma-ray bursts, or GRB, are the universe's most explosive events. Brief, blinding flashes of energy so intense that they outshine entire galaxies. In mere seconds, a single gamma-ray burst can release more energy than our sun will emit over its entire 10 billion-year lifetime. To put that into perspective, if a GRB occurred within a few thousand light-years of Earth, it could strip away our atmosphere and wipe out life as we know it. Fortunately, these cosmic fireworks happen far, far away, but their sheer power and mystery have captivated scientists for decades. So, what causes these titanic explosions? The leading theories point to two main culprits: the collapse of massive stars and the collision of neutron stars. When a star many times more massive than our sun exhausts its fuel, it doesn't just fade away, it collapses under its own gravity, triggering a supernova so violent that it produces a gamma-ray burst. These bursts are like the final, dramatic scream of a dying star, echoing across the cosmos. On the other hand, when two neutron stars, the dense remnants of dead stars, spiral into each other, their collision generates not only a gamma-ray burst, but also ripples in spacetime known as gravitational waves. It's a cosmic dance of destruction, one that we've only recently begun to witness. One of the most famous gamma-ray bursts, GRB 080319b, detected in 2008, was so bright that it was briefly visible to the naked eye, despite originating over 7.5 billion light-years away. This burst, nicknamed the Clark event, was a stark reminder of just how powerful these phenomena are. But GRBs aren't just awe-inspiring, they're also invaluable tools for studying the universe. Because they occur at such vast distances, their light travels through the cosmos for billions of years, carrying information about the early universe and the distribution of matter across space. Yet, gamma-ray bursts also challenge our understanding of stellar evolution and the limits of energy release. How can a single event produce so much energy so quickly? What mechanisms are at play in the heart of these explosions? These questions push the boundaries of astrophysics, forcing us to rethink our models of how stars live and die. And while we've made significant progress in detecting and analyzing GRBs, they remain one of the most elusive and enigmatic phenomena in the universe. As we grapple with the mysteries of gamma-ray bursts, another cosmic puzzle lies much closer to home: the Moon's magnetic anomalies. Unlike GRBs, these aren't explosive or fleeting, but they're just as baffling. The Moon, long thought to be a cold, dead world, hides pockets of magnetism that defy explanation. What could be causing these magnetic fields on a body with no global magnetic field of its own? That's a question we'll explore next, as we continue our journey through the universe's most perplexing mysteries. For now, gamma-ray bursts remind us that even in the darkest corners of space, there are flashes of brilliance, events so powerful they illuminate not just the cosmos, but also the limits of our understanding. The Moon, Earth's closest celestial companion, has long been seen as a quiet, unchanging world, a barren landscape of craters and dust. But hidden beneath its serene surface lies a mystery that defies expectations: lunar magnetic anomalies. These are patches on the moon's surface where the rock exhibits surprising magnetism, as if the moon has its own localized magnetic fields. This discovery is baffling because the moon, unlike Earth, doesn't have a global magnetic field today. So, how can these isolated regions of magnetism exist? The answer might rewrite what we know about the moon's history and its formation billions of years ago. One leading theory suggests that these magnetic anomalies could be remnants of ancient impacts. Imagine a massive asteroid slamming into the moon billions of years ago, when its core was still molten. The collision could have generated intense heat and pressure, creating localized magnetic fields that became frozen into the rock as it cooled. Alternatively, some scientists propose that the anomalies are tied to unique geological processes, such as the crystallization of iron-rich minerals in the moon's crust. These minerals, aligning in a specific way, could have produced magnetic fields that have persisted to this day. But why do these patches remain magnetic while the rest of the moon lost its magnetism long ago? That's the puzzle. What makes these anomalies even more intriguing is what they reveal about the moon's past. If they are indeed ancient, they could be windows into a time when the moon had a global magnetic field, something it hasn't had for billions of years. This would suggest that the moon's core was once much more active than it is today, possibly due to its proximity to a younger, more energetic Earth. Studying these magnetic patches could help us piece together the moon's early history and its relationship with our planet, offering clues about how both bodies evolved over time. But the mysteries don't end there. Some researchers have even speculated that these anomalies could be linked to rare, iron-rich meteorites that struck the moon, embedding magnetic material into its surface. Others suggest they might be evidence of long-lost volcanic activity, with lava flows cooling in a way that preserved their magnetic signatures. Each theory adds another layer to the mystery, challenging our understanding of the moon's geology and its place in the solar system. As we ponder the secrets of the moon's magnetic anomalies, another planetary enigma beckons: Saturn's hexagonal storm. This bizarre, six-sided vortex at the gas giant's north pole is unlike anything else in the solar system, a geometric wonder that defies explanation. How does such a perfect shape form in the chaotic atmosphere of a planet? That's a question we'll explore next as we continue to unravel the mysteries that make our solar system and the universe beyond so endlessly fascinating. For now, the moon's magnetic anomalies remind us that even the most familiar celestial bodies can hold surprises, urging us to look closer and question what we think we know. High above Saturn's north pole, a storm rages unlike anything else in the solar system, a perfect six-sided hurricane spinning with mathematical precision. Known as Saturn's hexagon, this colossal jet stream stretches over 30,000 kilometers wide, with winds reaching speeds of over 300 kilometers per hour. It's a mesmerizing geometric marvel, a natural phenomenon so precise that it almost looks artificial. But how can such a perfect shape exist in the chaotic, swirling atmosphere of a gas giant? That's the question that has puzzled scientists since the hexagon was first observed by the Voyager spacecraft in the early 1980s. What makes Saturn's hexagon so baffling is its sheer stability. Unlike storms on Earth, which are turbulent and ever-changing, this hexagonal pattern has persisted for decades, if not centuries, It's as if the atmosphere of Saturn has etched a permanent geometric signature into its skies. To put it simply, this isn't how fluids behave, at least, not according to our current understanding of fluid dynamics. On Earth, rotating fluids like air or water tend to form circular patterns, not polygons. So, what's causing this six-sided anomaly? The answer might lie deep within Saturn's atmosphere, where complex interactions between wind, temperature, and pressure create conditions unlike anything we've seen before. One leading theory suggests that the hexagon could be the result of standing wave patterns, similar to how vibrations on a guitar string create distinct notes. In this case, the string is Saturn's atmosphere, with the planet's rapid rotation and internal dynamics generating a stable, hexagonal wave. Another idea proposes that deep atmospheric processes, possibly involving the planet's core or magnetic field, could be shaping the storm. Some scientists even speculate that the hexagon might be driven by a combination of these factors, creating a unique equilibrium that allows the pattern to endure. Yet, despite decades of observation, the true cause remains elusive, a testament to the complexity of planetary atmospheres. Saturn's hexagon isn't just a scientific curiosity, it's a window into the fundamental physics of rotating fluids and atmospheric behavior. Studying it could help us understand not only Saturn, but also the atmospheres of other planets, including our own. It's a reminder that even in the familiar realms of our solar system, there are phenomena that challenge our understanding and ignite our curiosity. And as we marvel at this geometric wonder, another planetary mystery comes into view, one that defies expectations in an entirely different way: Venus' superrotation. While Saturn's hexagon captivates with its symmetry and stability, Venus presents a puzzle of motion. Its atmosphere races around the planet at speeds of up to 360 kilometers per hour, completing a full rotation in just 4 Earth days, despite the planet itself taking 243 days to spin once on its axis. How can an atmosphere move so much faster than the planet it surrounds? That's a question we'll explore next, as we continue to unravel the mysteries that make our solar system a place of endless wonder and discovery. Venus, often called Earth's twin due to its similar size and composition, holds a secret that makes it anything but ordinary. While its surface spins at a leisurely pace, taking 243 Earth days to complete a single rotation, its atmosphere races around the planet at breakneck speeds. This bizarre phenomenon, known as superrotation, sees Venus' atmosphere whipping around the planet in just 4 Earth days, nearly 60 times faster than the surface below. It's as if the planet's skies are in a perpetual hurry, defying everything we know about atmospheric behavior. But what could possibly drive such an extreme mismatch between the planet and its atmosphere? The key to understanding this mystery lies in Venus' unique environment. The planet is shrouded in a thick blanket of carbon dioxide, creating a runaway greenhouse effect that traps heat and drives surface temperatures to a scorching 470 degrees Celsius. This intense solar heating plays a critical role in powering the superrotation. As sunlight heats the atmosphere, it creates powerful winds that spiral around the planet, accelerated by the planet's slow rotation. But heat alone doesn't explain everything. Atmospheric waves, generated by the interaction of Venus topography and its dense atmosphere, also contribute to the phenomenon. These waves act like invisible conveyor belts, transferring energy and momentum to the upper atmosphere, where the winds are fastest. Scientists have used data from spacecraft like the European Space Agency's Venus Express and Japan's Akatsuki probe to study this process in detail. What they've found is a complex interplay of forces, where solar heating, atmospheric waves, and even the planet's thick cloud layers work together to create a system unlike anything seen on Earth or any other planet in our solar system. Yet, despite decades of research, the exact mechanisms driving superrotation remain a topic of debate. Some models suggest that turbulence within the atmosphere plays a significant role, while others point to the planet's lack of surface features, like oceans or mountains, which could otherwise slow down atmospheric motion. Venus' superrotation isn't just a fascinating oddity, it's a window into the fundamental physics of planetary atmospheres. By studying how Venus' atmosphere behaves, scientists can gain insights into weather systems on other planets, including Earth. It's a reminder that even in our own cosmic backyard, there are phenomena that challenge our understanding and push the boundaries of what we thought possible. As we leave behind the swirling skies of Venus, another cosmic mystery comes into focus: rogue planets. These are worlds untethered from any star, drifting through the darkness of interstellar space. Without the warmth of a sun, how do these lonely wanderers survive? And what can they tell us about the formation and evolution of planets? That's a story we'll explore next, as we continue our journey through the universe's most perplexing enigmas. For now, Venus' superrotation stands as a testament to the complexity of planetary atmospheres, urging us to look beyond the familiar and embrace the unknown. Imagine a planet with no sun, no dawn, no dusk, just endless darkness. These are rogue planets, celestial nomads wandering the galaxy untethered to any star. Unlike the planets in our solar system, which orbit the sun in predictable patterns, rogue planets drift freely through the void, untethered and unbound. They are the cosmic loners, challenging everything we thought we knew about what defines a planet. How do these worlds come to exist, and what secrets do they hold about the universe's most chaotic processes? The answers are as fascinating as they are mysterious. Rogue planets likely form in one of two ways. Some may have been born in the chaos of a young star system, only to be flung into deep space by gravitational interactions with larger planets or passing stars. Others might form directly from collapsing clouds of gas and dust, never having been part of a star system at all. These failed stars, sometimes called sub-brown dwarfs, blur the line between planets and stars, raising questions about how we classify celestial objects. What's clear is that rogue planets are far more common than we once thought. Recent studies suggest there could be billions of these solitary worlds drifting through the Milky Way, outnumbering stars by a significant margin. One of the most intriguing aspects of rogue planets is the possibility of life. Without a star to provide warmth, how could any form of life survive? Surprisingly, there are scenarios where it might be possible. Some rogue planets could retain heat from their formation, or through internal processes like radioactive decay, creating subsurface oceans beneath icy shells. These hidden oceans, shielded from the cold of space, could potentially harbor microbial life, much like the subsurface oceans suspected to exist on moons like Europa and Enceladus. While the idea of life on a rogue planet is speculative, it's a tantalizing thought, a reminder that life might find a way even in the most unlikely places. As we ponder the mysteries of these wandering worlds, another stellar oddity comes into view: hypervelocity stars. These are stars that move so fast they can escape the gravitational pull of their galaxies entirely. How do stars reach such incredible speeds, and what do they tell us about the forces at work in the universe? That's a story we'll explore next. For now, rogue planets stand as a testament to the universe's unpredictability, challenging our definitions and expanding our understanding of what it means to be a planet. In the vast expanse of space, even the loneliest worlds have stories to tell, stories that remind us just how diverse and surprising the cosmos can be. In the vast tapestry of the cosmos, where stars drift lazily through their galactic neighborhoods, there exists a rare breed of celestial objects that defy the norm. These are hypervelocity stars, stellar speedsters racing through space at millions of kilometers per hour, fast enough to break free from the gravitational grip of their galaxies entirely. Imagine a star moving so swiftly that it becomes a cosmic fugitive, destined to wander the intergalactic void forever. But how do stars reach such astonishing speeds, and what does their existence tell us about the forces shaping the universe? The story of hypervelocity stars begins with some of the most extreme environments in the cosmos, supermassive black holes. At the heart of most galaxies, including our own Milky Way, lies one of these gravitational behemoths. When a binary star system, a pair of stars, orbiting each other ventures too close to a supermassive black hole, the encounter can end in a dramatic ejection. The black hole's immense gravity captures one star, while the other is flung outward at incredible speeds, like a slingshot fired into the void. This process, known as the Hill's mechanism, is one of the primary ways hypervelocity stars are born. But it's not the only one. Galactic collisions, where two galaxies merge and stir up their stellar populations, can also launch stars into the abyss at breakneck speeds. What makes hypervelocity stars so fascinating isn't just their speed, but what they reveal about the universe. These runaway stars act as cosmic messengers, carrying clues about the environments that launched them. By tracing their paths, astronomers can map the gravitational landscapes of galaxies and uncover details about supermassive black holes that would otherwise remain hidden. Hypervelocity stars also challenge our understanding of galactic dynamics. Their existence suggests that galaxies aren't static structures but dynamic systems, constantly reshaped by gravitational interactions and collisions. In a way, these stars are a testament to the chaos and beauty of the cosmos, but the intrigue doesn't stop there. Some hypervelocity stars are thought to originate from outside the Milky Way, flung into our galaxy by similar processes in neighboring systems. These intergalactic travelers offer a glimpse into the broader cosmic web, hinting at the intricate connections between galaxies. They remind us that the universe is a vast, interconnected network, where even the smallest objects can carry profound implications. As we marvel at these stellar speedsters, another high-speed phenomenon comes into view: relativistic jets. These are narrow beams of particles shot from the vicinity of black holes and neutron stars, traveling at close to the speed of light. But how do these jets form, and what makes them so powerful? That's a story we'll explore next. For now, hypervelocity stars stand as a reminder of the universe's boundless energy and complexity, urging us to look beyond the familiar and embrace the extraordinary. In the grand dance of the cosmos, even the fastest stars are just one part of a much larger story, one that continues to unfold with every new discovery. From the chaotic hearts of black holes and neutron stars, where gravity is so intense it bends the very fabric of spacetime, come some of the most powerful and mysterious forces in the universe: relativistic jets. These are not your ordinary cosmic phenomena. Picture beams of particles, protons, electrons, and even entire atoms, being hurled into space at nearly the speed of light. These jets are so energetic that they can stretch for hundreds of thousands of light years, far beyond the boundaries of their host galaxies. But what could possibly produce such staggering amounts of energy? The answer lies in the extreme physics of some of the universe's most enigmatic objects. At the center of this cosmic spectacle are supermassive black holes and neutron stars. When matter falls toward a black hole, it doesn't just vanish into the void. Instead, it spirals into an accretion disk, a swirling, superheated maelstrom of gas and dust. As this material gets compressed and heated to unimaginable temperatures, magnetic fields twist and snap, launching jets of particles along the black hole's rotational axis. These jets are so powerful that they can outshine entire galaxies, becoming some of the brightest objects in the universe. Neutron stars, the dense remnants of exploded supernovae, can also produce relativistic jets, though on a smaller scale. In both cases, the energy released is mind-boggling, challenging our understanding of how matter and energy behave under such extreme conditions. What makes relativistic jets so fascinating is their ability to shape the cosmos on a grand scale. As these jets travel through space, they interact with the surrounding intergalactic medium, carving out vast cavities and heating the gas between galaxies. This process can halt star formation in some regions while triggering it in others, effectively steering the evolution of entire galaxies. In a way, relativistic jets are like cosmic sculptors, reshaping the universe one particle beam at a time. Yet, despite their immense power, many questions remain. How do these jets maintain their structure over such vast distances? What exactly accelerates the particles to near light speeds? Each discovery brings us closer to answers, but the full picture remains tantalizingly out of reach. Relativistic jets also serve as natural laboratories for testing the limits of physics. The conditions within these jets are so extreme that they defy our current understanding of matter and energy. For instance, the particles in these jets are accelerated to energies far beyond what we can achieve in even the most advanced particle colliders on Earth. Studying them could provide insights into fundamental questions about the nature of matter, the behavior of magnetic fields, and the interplay between gravity and electromagnetism. It's a reminder that the universe is not just a collection of stars and planets, but a dynamic, ever-changing arena where the laws of physics are pushed to their limits. As we marvel at the sheer power and mystery of relativistic jets, another phenomenon comes into focus, one that bends not particles, but light itself. Gravitational lensing, a cosmic effect predicted by Einstein's theory of general relativity, allows massive objects like galaxies and black holes to act as natural telescopes, magnifying and distorting the light from objects behind them. How does this bending of light reveal hidden corners of the universe? That's a question we'll explore next. For now, relativistic jets stand as a testament to the universe's ability to astonish, reminding us that even in the darkest depths of space, there are forces at work that defy imagination and redefine what we thought was possible. In the vast cosmic theater, where gravity and light perform an intricate dance, there's a phenomenon so extraordinary that it turns the universe into a natural magnifying glass. This is gravitational lensing, a breathtaking effect predicted by Einstein's theory of general relativity. Imagine a massive object, like a galaxy or a black hole, sitting between us and a distant light source. The immense gravitational pull of that object bends the fabric of spacetime, warping the path of light as it travels toward us. The result, a cosmic mirage, magnified, distorted, or even multiplied images of the distant object, as if the universe itself were playing tricks on our eyes. Gravitational lensing isn't just a visual spectacle, it's a powerful tool that challenges and deepens our understanding of gravity, Einstein's theory tells us that massive objects don't just attract matter, they also bend light. This bending creates what scientists call a gravitational lens, and it allows us to see objects that would otherwise be too faint or too far away to detect. One of the most famous examples is the Einstein cross, a quasar whose light has been split into 4 distinct images by the gravitational pull of a foreground galaxy. It's a stunning reminder of how gravity can act as both a sculptor and a telescope, revealing hidden corners of the cosmos. But gravitational lensing does more than just create beautiful images. It also provides crucial insights into one of the universe's greatest mysteries, dark matter. When astronomers observe lensed galaxies, they often find that the amount of visible matter doesn't account for the degree of bending. This discrepancy points to the presence of dark matter, an invisible substance that makes up about 85% of the universe's mass. By studying how light bends around massive objects, scientists can map the distribution of dark matter, piecing together its role in shaping the cosmos. In a way, gravitational lensing acts as a cosmic detective, uncovering clues about the unseen forces that govern the universe. One of the most remarkable examples of gravitational lensing is the Hubble Space Telescope's image of the galaxy cluster Abell 221-1. This cluster, known as the cosmic horseshoe, creates a stunning ring-like distortion of a background galaxy, magnifying it into a glowing arc. Such images not only captivate the imagination, but also provide invaluable data for studying the evolution of galaxies and the large-scale structure of the universe. Gravitational lensing reminds us that even the most distant and faint objects can be brought into focus, thanks to the interplay of gravity and light. As we marvel at the wonders of gravitational lensing, another light-related mystery comes into view, one that's shaping the very fate of the universe. Dark energy, an enigmatic force driving the accelerated expansion of the cosmos, challenges our understanding of physics on the grandest scale. How does this mysterious energy interact with light, and what does it tell us about the future of the universe? That's a story we'll explore next. For now, gravitational lensing stands as a testament to the universe's ability to surprise and enlighten, bending not just light, but also our perceptions of what's possible in the vast expanse of space. As we peer into the depths of the universe, there's an invisible force at work, one so powerful that it's shaping the very fate of the cosmos. This is dark energy, a mysterious entity that makes up about 68% of the universe and drives its accelerated expansion. Imagine the universe as a balloon, constantly inflating, with galaxies moving farther apart as the space between them stretches. But here's the twist. Instead of slowing down over time, this expansion is speeding up, defying the pull of gravity and challenging our understanding of how the universe works. Dark energy is the enigmatic force behind this cosmic acceleration, and its existence raises profound questions about the nature of reality itself. The discovery of dark energy came as a shock to scientists in the late 1990s. By studying distant supernovae, astronomers expected to find that the universe's expansion was slowing down due to gravity's pull. Instead, they found the opposite. The universe was expanding faster than ever. This unexpected revelation earned the researchers the Nobel Prize and turned cosmology on its head. Dark energy became the most plausible explanation for this accelerated expansion, but what exactly is it? The truth is, we don't know. Some theories suggest it could be a property of space itself, often referred to as the cosmological constant, an idea first proposed by Albert Einstein. Others propose it might be a dynamic field, similar to the Higgs field, but operating on a cosmic scale. Whatever its true nature, dark energy remains one of the greatest unsolved mysteries in science. Efforts to unravel the secrets of dark energy are ongoing, with telescopes and experiments designed to map the universe's expansion in unprecedented detail. Projects like the Dark Energy Survey and the upcoming Euclid space mission aim to measure the distribution of galaxies and the effects of dark energy over billions of years. These observations could provide clues about whether dark energy changes over time or remains constant, offering insights into the ultimate fate of the universe. Will the cosmos continue to expand forever, leading to a cold, dark end, or could dark energy evolve, potentially tearing galaxies and even atoms apart in a catastrophic Big Rip? These are the questions driving modern cosmology, and dark energy lies at the heart of them. But while dark energy pushes the universe apart, another mysterious force holds it together: dark matter. This invisible substance, which makes up about 27% of the universe, exerts a gravitational pull that binds galaxies and shapes the cosmic web. Together, dark energy and dark matter dominate the cosmos, yet we've barely begun to understand them. As we turn our attention to dark matter, we'll explore how it interacts with the universe and why its detection remains one of the most elusive challenges in modern science. For now, dark energy stands as a humbling reminder that the universe is far stranger than we imagined, a place where the most fundamental forces remain shrouded in mystery. And as we seek answers, we're reminded that every discovery brings new questions, deepening our awe of the cosmos and our place within it. While dark energy pushes the universe apart, there's another mysterious force silently holding it together: dark matter. This invisible substance, which makes up about 27% of the universe, is the cosmic glue that binds galaxies and shapes the vast web of cosmic structures. Unlike stars, planets, or even black holes, dark matter doesn't emit, absorb, or reflect light. It's completely invisible to our telescopes, yet its gravitational influence is unmistakable. Without dark matter, galaxies would fly apart, and the universe as we know it wouldn't exist. But what exactly is dark matter, and why does it remain so elusive? The answers could revolutionize our understanding of the universe. The story of dark matter begins with the unexpected behavior of galaxies. In the 1930s, astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving much faster than they should have been, based on the visible matter they contain. He proposed the existence of something unseen Dunkel Materie, or dark matter, to account for this discrepancy. Decades later, Vera Rubin's observations of spinning galaxies confirmed Zwicky's idea. She found that stars on the outer edges of galaxies were moving just as fast as those near the center, defying the laws of gravity as we understood them. The only explanation, a massive halo of invisible matter, exerting its gravitational pull but remaining hidden from view. So, what could dark matter be made of? The leading theory points to a class of hypothetical particles called WIMP, weakly interacting massive particles. These particles, if they exist, would interact with ordinary matter only through gravity and possibly the weak nuclear force, making them incredibly difficult to detect. Scientists have designed elaborate experiments to hunt for WIMP, using detectors buried deep underground to shield them from cosmic interference. Yet, despite decades of searching, dark matter particles have never been directly observed. This has led to alternative theories, such as actions or even modifications to the laws of gravity itself. Each possibility opens new doors to understanding the cosmos, but the mystery persists. The implications of dark matter extend far beyond its gravitational effects. It plays a crucial role in the formation and evolution of galaxies, acting as the scaffolding upon which visible matter accumulates. Without dark matter, the universe would lack the intricate structures we see today, from galaxy clusters to the cosmic web. Its discovery would not only solve one of the greatest puzzles in astrophysics, but also shed light on the fundamental nature of matter and energy. In a way, dark matter is the ultimate cosmic detective story, urging us to look beyond the visible and embrace the unknown. As we continue to search for dark matter, another invisible phenomenon comes into focus: cosmic rays. These high-energy particles, originating from deep space, bombard Earth's atmosphere constantly, carrying clues about the most violent events in the universe. From supernova explosions to black hole jets, cosmic rays offer a glimpse into the energetic processes that shape the cosmos. But how do these particles reach such incredible speeds, and what can they tell us about the universe's most extreme environments? That's a story we'll explore next. For now, dark matter stands as a testament to the universe's hidden complexity, a reminder that even the things we can't see hold the key to understanding the cosmos. In the search for answers, we're not just uncovering the secrets of dark matter, we're rewriting the story of the universe itself. Every second, Earth is bombarded by an invisible rain of particles traveling at nearly the speed of light. Cosmic rays. These high-energy particles, originating from some of the most violent events in the universe, zip through space and crash into our atmosphere, creating a cascade of secondary particles. While we can't see them, cosmic rays are everywhere, constantly streaming down from the cosmos. But where do they come from, and how do they reach such incredible speeds? The answers to these questions reveal a universe far more energetic and chaotic than we often imagine. Cosmic rays are primarily composed of protons, atomic nuclei, and other subatomic particles, accelerated to mind-boggling energies by extreme astrophysical processes. Some of these particles are thought to originate from supernova explosions, the violent deaths of massive stars. When a star explodes, it sends shockwaves rippling through space, accelerating particles to near light speeds. Other cosmic rays may come from even more exotic sources, like the jets of supermassive black holes or the remnants of gamma-ray bursts. These cosmic accelerators are so powerful that they can fling particles across the universe with energies millions of times greater than anything we can produce in particle colliders on Earth. But the mystery of cosmic rays doesn't stop at their origins. How exactly these particles are accelerated to such extreme speeds remains a topic of intense research. One leading theory involves what's known as Fermi acceleration, where particles gain energy by bouncing back and forth across shockwaves in space, like a pinball in a cosmic machine. Another possibility is that magnetic fields, twisted and amplified by turbulent environments, act as natural particle accelerators, propelling cosmic rays to their incredible velocities. Each discovery brings us closer to understanding these processes, but the full picture remains elusive, a reminder of the universe's complexity. While cosmic rays are fascinating in their own right, they also have a tangible impact on our planet. When these high-energy particles collide with Earth's atmosphere, they create showers of secondary particles, some of which reach the surface. This constant bombardment can affect satellite electronics, disrupt communication systems, and even pose risks to astronauts and high-altitude pilots. On a more positive note, cosmic rays have also played a role in shaping life on Earth. Some scientists believe that the mutations caused by these particles over millions of years may have influenced the evolution of life, adding another layer to their cosmic significance. As we uncover the secrets of these high-energy travelers, another phenomenon comes into focus, one that bends not just particles, but time itself. Time dilation, a concept rooted in Einstein's theory of relativity, reveals how the universe plays tricks with time depending on speed and gravity. How does time stretch and warp in the presence of extreme forces, and what does it tell us about the nature of reality? That's a question we'll explore next. For now, cosmic rays remind us that the universe is a place of constant motion and energy, where even the smallest particles can carry profound implications. In the grand tapestry of the cosmos, they are the silent messengers, carrying stories of the universe's most explosive events and challenging us to listen closely. Time, the steady, unyielding rhythm of our lives, turns out to be far more flexible than we ever imagined. Thanks to Einstein's theory of relativity, we now know that time isn't a universal constant. Instead, it's a malleable fabric that can stretch and warp depending on speed and gravity. This mind-bending phenomenon is called time dilation, and it challenges everything we think we know about how time flows. Imagine a clock ticking slower on a speeding spaceship or near a massive object like a black hole. While it sounds like science fiction, time dilation is very real, and its effects have been confirmed by countless experiments and real-world applications. At the heart of time dilation is the idea that time and space are interconnected, forming a single fabric known as spacetime. According to Einstein's theory, massive objects like planets and stars warp this fabric, creating what we experience as gravity. But this warping doesn't just affect space, it also affects time. Near a massive object, time slows down relative to a distant observer. Similarly, as an object moves faster, time for that object appears to slow down from the perspective of someone at rest. This isn't just theoretical. It's been proven through experiments like the famous Hayfel-Keating experiment, where atomic clocks flown on airplanes showed measurable differences in time compared to those left on the ground. One of the most practical examples of time dilation is found in the technology we use every day, GPS satellites. These satellites orbit Earth at incredibly high speeds, and their distance from the planet's gravitational field means time passes slightly faster for them than it does for us on the surface. If scientists didn't account for this difference, GPS calculations would be off by several kilometers within minutes. By adjusting for time dilation, we ensure the accuracy of everything from navigation apps to military operations. It's a perfect example of how a seemingly abstract concept has real-world consequences, shaping the way we interact with the world around us. But time dilation isn't just about satellites and clocks. It's a window into the fundamental nature of reality. It forces us to rethink our intuitive understanding of time as a steady, unchanging force. Instead, we see time as a dynamic, flexible dimension, intimately connected to the fabric of the universe. And as we grapple with the implications of time dilation, another relativistic phenomenon comes into focus, one where the warping of spacetime reaches its ultimate extreme. Black holes, the universe's most enigmatic objects, take the concept of time dilation to its limits, creating environments where time itself seems to stand still. But that's a story for another moment. For now, time dilation reminds us that the universe is far stranger and more wondrous than our everyday experiences suggest, urging us to look beyond the familiar and embrace the extraordinary. Black holes' cosmic enigmas so extreme that they bend the very fabric of reality. These are not just regions of space with strong gravity. They're places where gravity becomes so overwhelming that nothing, not even light, can escape. Imagine a point in the universe where the rules of physics as we know them break down, where time and space are twisted beyond recognition. This is the realm of black holes, and it's one of the most fascinating and terrifying phenomena in the cosmos. From their mysterious event horizons to their infinitely dense singularities, black holes challenge everything we think we know about the universe. At the heart of every black hole lies the event horizon, the boundary beyond which escape is impossible. Think of it as a one-way door. Once something crosses this threshold, it's gone forever, swallowed by the black hole's immense gravitational pull. But the event horizon isn't just a point of no return, it's also a place where the laws of physics start to unravel. Here, time slows to a crawl, and space becomes infinitely curved. It's a cosmic paradox, a place where our understanding of reality is pushed to its limits. Deeper still lies the singularity, the black hole's core. At this point, all the matter that falls into the black hole is crushed into an infinitely dense point, a place where gravity becomes infinite and the laws of physics as we know them cease to apply. The singularity is a mystery wrapped in an enigma, a point where our current theories of gravity and quantum mechanics collide, leaving us with more questions than answers. What happens at the center of a black hole? Does matter truly disappear, or is it transformed into something entirely new? These are questions that continue to baffle even the brightest minds in physics. But black holes aren't just theoretical curiosities, they're very real, and we've begun to see them in ways we never thought possible. In 2019, the Event Horizon Telescope collaboration unveiled the first ever image of a black hole located at the center of the galaxy M87. This groundbreaking image, showing a glowing ring of light surrounding a dark shadow, confirmed decades of predictions and opened a new chapter in our understanding of these cosmic giants. It was a moment that captured the world's imagination, proving that even the most elusive objects in the universe can be brought into view with ingenuity and perseverance. As we continue to study black holes, they reveal not just the extremes of gravity, but also the limits of our knowledge. They are cosmic laboratories, testing the boundaries of physics and challenging us to rethink our understanding of space, time, and matter. And while black holes dominate the conversation about extreme objects in the universe, they're not the only ones. Just as mysterious and equally fascinating are neutron stars, the dense remnants of massive stars that have exploded in supernovae. These stellar relics pack the mass of a star into a city-sized object, creating conditions so extreme that a teaspoon of neutron star material would weigh billions of tons. But that's a story for another moment. For now, black holes stand as a testament to the universe's ability to defy logic and ignite our curiosity, reminding us that even in the darkest corners of space, there are wonders waiting to be uncovered. While black holes captivate with their inescapable gravity, there's another cosmic marvel born from the ashes of stellar explosions: neutron stars. These are the remnants of massive stars that have exhausted their fuel and collapsed in a spectacular supernova. Picture squeezing the mass of our sun into a sphere just 20 kilometers across, small enough to fit inside a city. The result is an object so dense that a single teaspoon of its material would weigh billions of tons. Neutron stars are not just exotic leftovers, they're cosmic laboratories, pushing the boundaries of what we know about matter and the forces that govern it. What makes neutron stars so extraordinary is their density. When a massive star collapses, its core is compressed to such an extreme degree that protons and electrons merge, forming neutrons. This creates a state of matter unlike anything found on Earth, a neutron-rich soup where the rules of nuclear physics are rewritten. The gravitational pull on a neutron star is so intense that if you were to drop an object from just 1 meter above its surface, it would hit the ground at half the speed of light. These conditions are so extreme that they challenge our understanding of how matter behaves under pressure, offering a glimpse into the fundamental nature of the universe. But neutron stars aren't just dense, they're also incredibly dynamic. Some neutron stars rotate at mind-boggling speeds, completing hundreds of revolutions every second. These rapidly spinning stars, known as pulsars, emit beams of radiation from their magnetic poles. As the star spins, these beams sweep across space like cosmic lighthouses, creating periodic pulses of light that can be detected from Earth. The first pulsar discovered, PSRB 1919+21, was initially nicknamed the Little Green Men because its regular signals were so precise that astronomers wondered if they were artificial. Today, pulsars are invaluable tools for studying the cosmos, helping us map the Milky Way and even detect gravitational waves. Then there are magnetars, a special class of neutron stars with magnetic fields trillions of times stronger than Earth. These fields are so powerful that they can distort the structure of atoms and rip apart molecules from thousands of kilometers away. Magnetars occasionally release bursts of energy so intense that they can be detected across the galaxy, flaring up in seconds and then fading just as quickly. These outbursts are among the most energetic events in the universe, rivaling even supernovae in their intensity. Yet, despite their power, magnetars remain shrouded in mystery, their behavior defying many of our current models of physics. As we marvel at the extremes of neutron stars, another dense stellar remnant comes into focus: white dwarfs. These are the remnants of stars like our Sun, which, after exhausting their fuel, shed their outer layers and collapse into a dense core. But how do white dwarfs compare to neutron stars? And what secrets do they hold about the life cycles of stars? That's a question we'll explore next. For now, neutron stars stand as a testament to the universe's ability to transform destruction into creation, turning the violent deaths of stars into some of the most fascinating objects in the cosmos. They remind us that even in the aftermath of chaos, there's beauty, wonder, and endless opportunities for discovery. While neutron stars are born from the explosive deaths of massive stars, another stellar remnant quietly takes its place in the cosmic tapestry: white dwarfs. These are the final stages of stars like our Sun, the glowing embers left behind after a star has burned through its fuel and shed its outer layers. Picture a star that once shone brightly, now condensed into an Earth-sized sphere, glowing faintly with the residual heat of its former life. But don't let their small size fool you. White dwarfs are incredibly dense, packing the mass of a star into a volume no larger than a planet. They are the quiet survivors of stellar evolution, but their cooling processes and eventual fate hold secrets that challenge our understanding of the universe. When a star like our Sun exhausts its nuclear fuel, it swells into a red giant, engulfing nearby planets before shedding its outer layers in a gentle, glowing cloud called a planetary nebula. What remains is the star's core, now a white dwarf. These remnants are supported not by nuclear fusion, but by a quantum mechanical effect called electron degeneracy pressure, a force so strong it prevents the star from collapsing further under its own gravity. Over billions of years, white dwarfs slowly cool and fade, their light dimming as they radiate away their stored heat. Eventually, they become black dwarfs, cold, dark relics of stars that once illuminated the cosmos. But here's the catch: the universe isn't old enough for any black dwarfs to exist yet. Every white dwarf we've observed is still in the process of cooling, a reminder of the slow, inexorable march of time. White dwarfs aren't just endpoints in stellar evolution, they're also key players in some of the universe's most spectacular events. When a white dwarf in a binary system pulls matter from its companion star, it can accumulate enough mass to trigger a cataclysmic explosion known as a Type Ia supernova. These supernovae are so bright they can outshine entire galaxies, and their consistent luminosity makes them invaluable tools for measuring cosmic distances. In fact, it was observations of Type Ia supernova that first revealed the accelerating expansion of the universe, leading to the discovery of dark energy. In a way, white dwarfs are cosmic storytellers, their explosive deaths revealing profound truths about the nature of reality. Yet, even as they illuminate the cosmos, white dwarfs challenge our understanding of stellar life cycles. For instance, some white dwarfs exhibit strange chemical compositions, with traces of elements like carbon and oxygen at their surfaces. Others have been found with atmospheres rich in helium or hydrogen, defying expectations about how these remnants should evolve. These anomalies raise questions about the processes that occur during a star's final stages, hinting at complexities we've yet to fully unravel. White dwarfs may be the quiet remnants of stars, but they are far from simple. As we ponder the mysteries of white dwarfs and their eventual fade into darkness, another cosmic phenomenon comes into view, one that's anything but quiet. Supernovae, the explosive deaths of stars, are some of the most energetic events in the universe, scattering the building blocks of life across the cosmos. But what exactly happens during a supernova, and how do these cataclysmic explosions shape the universe as we know it? That's a question we'll explore next. For now, white dwarfs stand as a testament to the quiet yet profound role stars play in the universe, their fading light a reminder that even in endings, there is both beauty and mystery. Supernovae are the universe's grandest fireworks, spectacular explosions that mark the dramatic end of a massive star's life. When a star many times more massive than our Sun exhausts its nuclear fuel, it doesn't fade quietly. Instead, it collapses under its own gravity and then rebounds in an explosion so powerful it can outshine an entire galaxy. In a matter of seconds, a supernova releases more energy than the Sun will emit over its entire 10 billion-year lifetime. But these explosions aren't just dazzling cosmic displays, they're fundamental to the story of the universe, shaping galaxies, creating the building blocks of life, and challenging our understanding of how stars live and die. At the heart of a supernova is a process of unimaginable violence. When a massive star can no longer support itself against gravity, its core collapses, triggering a shock wave that rips through the star's outer layers. This shockwave flings material into space at incredible speeds, scattering heavy elements like iron, gold, and uranium across the cosmos. In fact, nearly every element heavier than iron, the metals that make up planets, jewelry, and even our own bodies, was forged in the hearts of exploding stars. Supernovae are the universe's ultimate alchemists, transforming simple elements into the complex materials that make life possible. Without them, the periodic table would be far emptier, and the universe as we know it wouldn't exist. But supernovae do more than just create elements. They also shape the evolution of galaxies. The energy and shock waves from these explosions can trigger the formation of new stars by compressing nearby gas clouds, setting off a chain reaction of stellar birth and death. This cycle of destruction and creation is what drives the dynamic nature of galaxies, ensuring that they don't remain static but instead evolve over billions of years. Supernova are cosmic sculptors, carving out the structures we see in the universe today and seeding the cosmos with the ingredients for future stars, planets, and perhaps even life. Yet for all their power and importance, supernova remain shrouded in mystery. While we've observed many of these explosions, the exact mechanisms that trigger them are still not fully understood. Why do some stars explode in such spectacular fashion, while others collapse quietly into black holes or neutron stars? What role do magnetic fields, rotation, or the star's composition play in determining its fate? These are questions that continue to challenge astronomers, pushing them to refine their models and develop new ways to observe these cataclysmic events. As we marvel at the explosive power of supernova, another phenomenon comes into focus, one that's even rarer and more energetic. Kilonovae, the result of neutron star collisions, are cosmic events that combine the brilliance of a supernova with the precision of a cosmic collision. But what exactly happens when two neutron stars collide, and how do these events contribute to the universe's chemical makeup? That's a story we'll explore next. For now, supernova stand as a testament to the universe's ability to create through destruction, reminding us that even in the most violent events, there is beauty, wonder, and the seeds of new beginnings. When two neutron stars collide, the universe doesn't just witness a collision, it experiences a cosmic spectacle unlike anything else. These cataclysmic events, known as kilonovae, are among the most energetic phenomena in the cosmos, producing brilliant flashes of light and ripples in spacetime called gravitational waves. But kilonovae aren't just dazzling displays, they're cosmic forges, creating the heaviest elements in the universe, elements like gold, platinum, and uranium. These rare and violent mergers challenge our understanding of how matter is created and distributed across the cosmos, offering a glimpse into the origins of the very materials that make up our world. The story of a kilonova begins with two neutron stars, the ultra-dense remnants of massive stars that have exploded in supernova. As these stellar corpses spiral closer together, their immense gravitational pull distorts spacetime, sending out gravitational waves, ripples that travel across the universe at the speed of light. When the stars finally collide, the impact is so powerful that it triggers a massive explosion, releasing energy equivalent to 1 billion suns. But unlike a supernova, which lasts for weeks, a kilonova's light fades within days, leaving behind a lingering glow rich in heavy elements. It's as if the universe has performed a brief, intense alchemy, transforming the simplest elements into the rarest metals. What makes kilonovae so groundbreaking is their role in nucleosynthesis, the process by which elements are formed. While lighter elements like hydrogen and helium were created during the Big Bang, and heavier ones like carbon and oxygen are forged in the hearts of stars, the heaviest elements require something far more extreme. Kilonovae provide the perfect conditions for this process, known as rapid neutron capture, or the R process. In the chaotic aftermath of a neutron star collision, free neutrons bombard atomic nuclei, building up elements like gold and platinum in a matter of seconds. Without these violent mergers, the periodic table would be missing some of its most valuable and fascinating elements. But kilonovae aren't just about heavy elements, they're also pioneers in a new era of astronomy. In 2017, scientists made history by observing a kilonova in both gravitational waves and light, a groundbreaking achievement known as multi-messenger astronomy. This event, dubbed GW 170817, marked the first time astronomers combined gravitational wave data with traditional observations, opening a new window into the universe. By studying Kilonovae, we're not just learning about the origins of elements, we're also uncovering the secrets of neutron stars, gravitational waves, and the forces that shape the cosmos. As we marvel at the brilliance of Kilonovae, another gravitational phenomenon comes into focus, one that's equally transformative but far more subtle. Gravitational waves, the ripples in spacetime first predicted by Einstein, have revolutionized our ability to observe the universe. Unlike light, which can be blocked or distorted, gravitational waves travel unimpeded, carrying information about the most violent events in the cosmos. But how do these ripples form, and what do they reveal about the universe's most extreme environments? That's a question we'll explore next, as we continue to unravel the mysteries that make the cosmos a place of endless discovery and wonder. For now, Kilonovae stand as a testament to the universe's ability to create beauty from chaos, reminding us that even in the most violent collisions, there are seeds of creation waiting to be discovered. Gravitational waves are the whispers of the cosmos, ripples in the very fabric of spacetime itself. These elusive signals are born from some of the most violent and energetic events in the universe, colliding black holes, merging neutron stars, and even the explosive birth of the cosmos during the Big Bang. Unlike light, which can be blocked or absorbed, gravitational waves travel unimpeded, carrying with them the secrets of the universe's most extreme environments. Their discovery has opened a whole new way of observing the cosmos, one that doesn't rely on light, but instead on the subtle distortions of spacetime itself. The story of gravitational waves begins with Albert Einstein, who predicted their existence over a century ago as part of his theory of general relativity. According to Einstein, massive objects like black holes and neutron stars warp the fabric of spacetime, and when these objects move or collide, they send ripples outward, much like a stone dropped in a pond. For decades, detecting these ripples seemed nearly impossible. They were so faint that even Einstein doubted we'd ever observe them, but in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, achieved the impossible. For the first time, scientists detected gravitational waves from the collision of two black holes over 1 billion light-years away. It was a moment that changed astronomy forever. Since that groundbreaking discovery, LIGO and its European counterpart, Virgo, have detected dozens of gravitational wave events, each one offering new insights into the universe. These observatories work by using laser beams to measure tiny distortions in spacetime changes, so minuscule they're equivalent to detecting a hair's width shift in the distance to the nearest star. Through these detections, we've witnessed the mergers of black holes, the collisions of neutron stars, and even the echoes of cosmic events that occurred billions of years ago. Gravitational waves have given us a front-row seat to the universe's most dramatic performances that were once invisible to us. But the implications of gravitational waves go far beyond just observing cosmic collisions. They challenge our understanding of gravity itself, testing Einstein's predictions in ways that were previously unimaginable. For instance, the precise measurements of gravitational waves have allowed scientists to confirm that black holes behave exactly as Einstein's equations predict, even under the most extreme conditions. They've also provided evidence for the existence of intermediate mass black holes, a class of black holes that had long eluded detection. In a way, gravitational waves are like cosmic detectives, uncovering clues about the universe's most enigmatic objects and the forces that govern them. As we continue to listen to the universe's gravitational symphony, another space-time mystery comes into view, one that's equally captivating but far more speculative. Wormholes, hypothetical tunnels through space-time, could theoretically allow travel between distant points in the universe, or even between universes. But what exactly are wormholes, and could they really exist? That's a question we'll explore next, as we venture into the realm of theoretical physics and the tantalizing possibilities it holds. For now, gravitational waves remind us that the universe speaks in more ways than one, and with each new ripple we detect, we're learning to listen more closely to its secrets. Wormholes, these hypothetical tunnels through spacetime, have long captured the imagination of scientists and science fiction fans alike. Imagine a shortcut through the universe, a cosmic bridge that could connect distant regions of space or even different points in time. These theoretical passages, also known as Einstein-Rosen bridges, emerge as solutions to Einstein's equations of general relativity. But are they real or just fascinating mathematical quirks? The answer lies at the intersection of gravity, quantum mechanics, and the deepest mysteries of the cosmos. At their core, wormholes are like cosmic gateways, bending the fabric of spacetime so dramatically that two distant points become connected. Picture folding a piece of paper so that two dots on opposite sides touch. That's the basic idea. In theory, a wormhole could allow travel between these points faster than light could traverse the normal distance. But here's the catch. Wormholes, as predicted by general relativity, are incredibly unstable. Without some form of exotic matter to hold them open, a substance with negative energy or mass, they would collapse almost instantly. This requirement pushes the boundaries of physics, challenging our understanding of what's possible in the universe. The implications of wormholes are staggering. If they could exist and be stabilized, they might enable interstellar travel, allowing us to cross vast cosmic distances in an instant. They could also, in theory, facilitate time travel, creating loops in spacetime that challenge our notions of cause and effect. But these possibilities come with a host of paradoxes and unanswered questions. For instance, could a wormhole allow you to travel back in time and alter history? Such scenarios push the limits of our current theories, leaving scientists to grapple with the complexities of quantum mechanics and gravity. Despite their allure, wormholes remain purely theoretical. No observational evidence has been found to suggest they exist, and the exotic matter required to stabilize them has never been detected. Yet, their study continues to inspire breakthroughs in theoretical physics, offering insights into the nature of spacetime and the potential unification of quantum mechanics and general relativity. Wormholes remind us that the universe is full of possibilities, even if some remain tantalizingly out of reach. As we ponder the mysteries of wormholes and their potential to rewrite the rules of spacetime, another phenomenon emerges, one that bridges the gap between quantum mechanics and black holes. Hawking radiation, the faint glow predicted to emanate from black holes, challenges our understanding of these cosmic giants and the nature of reality itself. But how does this radiation work, and what does it reveal about the universe's most enigmatic objects? That's a story we'll explore next, as we continue our journey through the cosmos, uncovering the secrets that make it a place of endless wonder. For now, wormholes stand as a testament to the power of imagination and the boundless curiosity that drives us to explore the unknown. Black holes, the universe's ultimate vacuum cleaners, are supposed to trap everything that crosses their event horizon, or so we thought. But what if black holes aren't entirely black? What if they're slowly leaking energy, fading away over eons like cosmic candles? This is the mind-bending idea behind Hawking radiation, a theoretical phenomenon predicted by physicist Stephen Hawking in the 1970s. It's a concept that not only challenges our understanding of black holes, but also blurs the line between quantum mechanics and gravity, two of the most fundamental and seemingly incompatible theories in physics. At the heart of Hawking radiation is a quantum quirk known as particle-antiparticle pairs. In the quantum realm, empty space isn't truly empty. Instead, it's a bubbling sea of virtual particles that constantly pop into existence and annihilate each other. Normally, this dance happens too quickly for us to notice, but near the event horizon of a black hole, things get strange. Gravity is so intense that one particle in the pair can fall into the black hole while the other escapes into space. The escaping particle becomes real, carrying away energy, and in the process, causing the black hole to lose mass. Over unimaginable spans of time, this process could cause a black hole to evaporate completely, leaving behind nothing but a faint whisper of radiation. This idea turns black holes from eternal prisons into fading echoes, but it also raises profound questions about the nature of information. According to quantum mechanics, information about the state of a system can never be truly lost. But if a black hole evaporates, what happens to all the information about the matter it consumed? This dilemma, known as the black hole information paradox, remains one of the greatest unsolved problems in physics. Some scientists suggest that the information might be encoded in the Hawking radiation itself, while others propose entirely new frameworks, like the holographic principle, to reconcile the conflict. Whatever the answer, Hawking radiation forces us to rethink the very nature of reality, pushing the boundaries of both quantum theory and general relativity. The implications of Hawking radiation extend far beyond black holes. If it exists, it could provide a crucial link between quantum mechanics and gravity, two theories that have long resisted unification. It also hints at the ultimate fate of black holes, suggesting that even these cosmic giants are not immune to the relentless march of time. And while Hawking radiation has yet to be directly observed, its theoretical foundations are so compelling that many physicists believe it's only a matter of time before we find evidence. But as we grapple with the mysteries of Hawking radiation, another quantum phenomenon comes into view, one that's just as strange and just as profound. Quantum entanglement, the eerie connection between particles that defies our classical understanding of space and time, challenges our notions of reality in ways that even black holes can't. What happens when two particles become so deeply linked that measuring one instantly affects the other, no matter how far apart they are? That's a question we'll explore next, as we continue our journey through the universe's most mind-bending mysteries. For now, Hawking radiation stands as a testament to the universe's ability to surprise us, reminding us that even the darkest corners of space hold the promise of light and the keys to unlocking the deepest secrets of existence. Now, let's step into the strange and counterintuitive world of quantum entanglement, a phenomenon so bizarre that even Albert Einstein famously called it spooky action at a distance. Imagine two particles, perhaps electrons or photons, that become so deeply connected that the state of one instantly influences the state of the other, no matter how far apart they are. It's as if they share an invisible bond that defies the limits of space and time. This isn't science fiction, it's quantum mechanics at its most perplexing, and it's rewriting the rules of how we think about reality. At the heart of quantum entanglement is the idea that particles can be linked in such a way that their properties like spin, polarization, or momentum are correlated. When you measure one particle, the other instantly knows and adjusts its state accordingly, even if it's light years away. This instantaneous connection seems to violate the principle of locality, the idea that objects are only influenced by their immediate surroundings. It also challenges our understanding of causality, the notion that cause must precede effect. How can two particles communicate faster than the speed of light, a limit that Einstein's theory of relativity says nothing can surpass? This paradox has puzzled physicists for decades, and it's one of the key reasons quantum mechanics remains so deeply mysterious. But quantum entanglement isn't just a theoretical curiosity. It has real-world applications that could revolutionize technology. One of the most promising is quantum computing. Unlike classical computers, which process information in binary bits, zeros and ones, quantum computers use qubits, which can exist in multiple states at once thanks to superposition. Entangled qubits can work together in ways that allow quantum computers to solve complex problems like simulating molecules or cracking encryption codes far faster than any classical machine. Similarly, quantum communication relies on entanglement to create ultra-secure networks where information can't be intercepted without being detected. These technologies are still in their infancy, but they hold the potential to transform industries and reshape our digital world. Despite its potential, quantum entanglement raises profound questions about the nature of reality. Does it mean that the universe is fundamentally interconnected in ways we don't yet understand? Or does it suggest that our classical notions of space and time are incomplete? Physicists are still grappling with these questions, and each new experiment brings us closer to answers, or perhaps deeper into the mystery. What's clear is that entanglement forces us to rethink the very fabric of the universe, revealing a cosmos far stranger and more interconnected than we ever imagined. As we delve into the implications of quantum entanglement, another quantum phenomenon emerges, one that's equally mysterious and even more fundamental to the nature of space itself. Vacuum energy, the energy inherent in empty space, suggests that the vacuum of space isn't truly empty but teeming with activity. What does this mean for our understanding of the universe, and how does it connect to the enigmatic force known as dark energy? That's a question we'll explore next, as we continue to unravel the quantum mysteries that shape our reality. For now, quantum entanglement stands as a testament to the universe's ability to defy intuition, challenging us to see the cosmos not as a collection of separate objects, but as a deeply interconnected tapestry of possibilities. At the heart of the quantum world lies a concept so strange, it turns the very idea of nothingness on its head. This is vacuum energy, the energy that permeates empty space. Far from being an inert void, the vacuum of space is a seething, dynamic arena where particles flicker in and out of existence in a dance dictated by the laws of quantum mechanics. These fleeting particles, known as virtual particles, are the hallmark of vacuum energy, and they reveal a universe where even the emptiest regions are teeming with activity. But what does this mean for our understanding of space, time, and the cosmos itself? Vacuum energy arises from the principles of quantum field theory, which describes the universe as a collection of fields that fill all of space. Even in the absence of matter, these fields are never truly still. Instead, they fluctuate constantly, producing pairs of virtual particles that appear and vanish in an instant. These fluctuations are so fundamental that they are often referred to as the zero-point energy of the vacuum, a baseline level of energy that can never be removed. It's as if the universe itself hums with a faint, eternal vibration, a reminder that emptiness is anything but empty. But vacuum energy isn't just a curious quirk of quantum mechanics, it has profound implications for the cosmos. One of the most startling is its connection to the expansion of the universe. According to Einstein's theory of general relativity, vacuum energy exerts a kind of repulsive force, pushing space itself apart. This effect, known as dark energy, is thought to be responsible for the accelerating expansion of the universe. In fact, vacuum energy is often equated with the cosmological constant, a term Einstein introduced into his equations to describe a static universe but later abandoned. Ironically, it's now seen as one of the most important factors shaping the fate of the cosmos. Yet, there's a problem. When physicists try to calculate the amount of vacuum energy predicted by quantum field theory, they arrive at a number that's staggeringly larger than what we observe in the universe. This discrepancy, known as the cosmological constant problem, is one of the greatest unsolved puzzles in modern physics. How can the theoretical prediction of vacuum energy be so wildly off from what we measure? Some scientists suggest that there might be unknown mechanisms at work, canceling out most of the vacuum energy and leaving behind the small amount we detect. Others propose entirely new frameworks, such as string theory or modifications to quantum mechanics, to resolve the issue. Whatever the answer, vacuum energy forces us to confront the limits of our current understanding and rethink the very nature of the universe. As we grapple with the mysteries of vacuum energy and its role in the cosmos, another tantalizing possibility emerges, one that takes us beyond the boundaries of our own universe. The multiverse theory suggests that our universe might be just one of countless others, each with its own unique laws of physics and constants. Could vacuum energy play a role in shaping these other universes? And if so, what does that mean for our place in the grand scheme of reality? These are questions that push the boundaries of science and imagination, reminding us that the universe is full of surprises and that even the emptiest spaces are brimming with potential. Imagine a reality where every decision you've ever made, every path you've chosen or avoided has played out in a parallel universe, a place where the laws of physics might be completely different, where stars never formed, or where life evolved in ways we can't even fathom. This isn't the plot of a sci-fi movie, it's the multiverse, a mind-bending concept that suggests our universe might be just one of countless others. It's an idea that challenges everything we think we know about cosmology, reality, and our place in the cosmos. But could the multiverse really exist, and what does it mean for our understanding of the universe? The multiverse isn't a single, unified theory, but rather a collection of ideas that all point to the possibility of multiple universes. One of the most compelling frameworks comes from string theory, which suggests that the fabric of reality is made up of tiny, vibrating strings. These strings exist in higher dimensions beyond the three we're familiar with, and different configurations of these strings could give rise to entirely separate universes, each with its own unique laws of physics. Imagine these universes as bubbles floating in a vast cosmic foam, each one a self-contained reality, completely isolated from the others. It's a concept that stretches the imagination, but it's rooted in some of the most advanced mathematical models we have. Another key piece of the multiverse puzzle comes from inflationary cosmology, which describes the rapid expansion of the universe just moments after the Big Bang. According to this theory, inflation didn't just happen once. It's ongoing, creating new, pocket universes in an endless cycle of expansion. Each of these universes could have different physical constants, particles, and forces, making them as diverse as the stars in the sky. Some might be barren, devoid of life, while others could be teeming with civilizations far more advanced than our own. The sheer scale of this idea is humbling, suggesting that our universe might be just one tiny speck in an infinite cosmic ocean. But the multiverse isn't without its critics. Some argue that it's untestable, falling outside the realm of science because we can't observe or interact with these other universes. Yet, proponents counter that the multiverse could explain some of the biggest mysteries in physics, like why the constants of nature, such as the speed of light or the strength of gravity, are so finely tuned to allow life to exist. If there are infinite universes, it's almost inevitable that at least one would have the right conditions for life. This anthropic principle offers a tantalizing solution to one of cosmology's most perplexing questions, even if it raises plenty of others. As we grapple with the implications of the multiverse, another fundamental mystery comes into focus, one that's deeply tied to our experience of reality: the arrow of time. Why does time move forward, and what gives it its unidirectional flow? From the multiverse's infinite possibilities to the relentless march of time, the cosmos continues to challenge our understanding, reminding us that every answer leads to new questions. And as we explore these mysteries, we're not just learning about the universe, we're discovering how much there is left to uncover. The multiverse, with its infinite possibilities, stands as a testament to the boundless curiosity that drives us to explore the unknown, pushing the limits of what we think is possible and redefining our place in the grand tapestry of existence. Time, it's the one constant in our lives, ticking forward with unyielding precision, shaping everything from the rhythms of nature to the unfolding of history. But have you ever stopped to wonder why time moves in only one direction? Why can we remember the past but not the future? This is the mystery of the arrow of time, a concept so fundamental yet so deeply puzzling that it challenges our understanding of physics, thermodynamics, and even the origins of the universe itself. At its core, the arrow of time is the idea that time has a preferred direction, flowing from the past into the future. This might seem obvious after all. We can't unbreak an egg or unburn a piece of toast, but it raises profound questions about the nature of reality. Why does time move forward and not backward? And why does it seem to have such a clear, one-way flow? The answers lie in one of the most fundamental principles of physics: entropy. Entropy, in simple terms, is a measure of disorder in a system. The second law of thermodynamics tells us that in any closed system, entropy always increases over time. This is why a cup of hot coffee cools down but never spontaneously heats up, or why a tidy room becomes messy but never organizes itself. The universe, as a whole, is constantly moving toward higher entropy, and this relentless march toward disorder is what gives time its arrow. The past is a state of lower entropy, the future a state of higher entropy, but here's the twist: while the laws of physics are symmetric, meaning they work the same whether time runs forward or backward, the arrow of time is not. This asymmetry is one of the great unsolved puzzles of science. The origins of the arrow of time may lie in the Big Bang. At the moment of the universe's birth, everything was in an incredibly low entropy state, a highly ordered, dense, and hot beginning. As the universe expanded and cooled, entropy began to increase, setting the stage for the arrow of time we experience today. But why did the universe start in such a low entropy state? Was it simply a cosmic accident, or is there a deeper reason? These are questions that continue to challenge physicists, pushing them to explore the very foundations of reality. Yet, even as we grapple with the arrow of time, another temporal mystery emerges, one that seems to defy the very nature of time itself. Time crystals, a bizarre state of matter first theorized in 2012, exhibit motion in their ground state, repeating patterns in time without expending energy. It's as if they've found a way to dance to the beat of time, breaking the rules of thermodynamics in the process. What are these strange structures, and how do they challenge our understanding of time and matter? That's a question we'll explore next, as we continue to unravel the mysteries that make the universe a place of endless discovery and wonder. For now, the arrow of time stands as a testament to the universe's relentless march toward complexity, reminding us that even the most familiar aspects of reality can hold secrets waiting to be uncovered. Now, let's step into the realm of the truly bizarre, a world where matter doesn't just exist in space, but dances through time itself. Meet time crystals, a groundbreaking discovery that defies the very laws of thermodynamics and redefines what we thought was possible in the universe. Unlike ordinary crystals, which have a repeating pattern in space like the lattice of a diamond, time crystals repeat their structure in time. Imagine a clock that ticks forever without any external energy, a perpetual motion machine powered by the strange rules of quantum mechanics. This isn't science fiction. It's a real phenomenon that's shaking up the foundations of physics. The concept of time crystals was first proposed in 2012 by Nobel laureate Frank Wilczek, who imagined a state of matter that could exhibit periodic motion in its ground state, its lowest energy configuration. Normally, such motion would require energy, but time crystals somehow manage to oscillate without any input, breaking the symmetry of time itself. This idea was initially met with skepticism, but in 2017, two independent teams of scientists successfully created time crystals in the lab using chains of ions and quantum systems. These experiments confirmed that time crystals aren't just theoretical curiosities, they are real, and they're opening up entirely new avenues of research. What makes time crystals so revolutionary is how they challenge our understanding of symmetry and quantum mechanics. In physics, symmetry is a cornerstone principle, governing everything from the behavior of particles to the structure of the universe. Time crystals, however, break time translation symmetry, the idea that the laws of physics remain the same at all moments in time. Instead, they oscillate in a predictable, repeating pattern, creating a kind of temporal order that's never been seen before. This discovery not only deepens our understanding of quantum systems, but also hints at new possibilities for exotic states of matter that we've yet to imagine. But time crystals aren't just fascinating from a theoretical perspective, they also hold immense practical potential. One of the most exciting applications lies in the field of quantum computing. Quantum computers rely on qubits, which are notoriously fragile and prone to decoherence, the loss of quantum information due to external interference. Time crystals, with their stable, self-sustaining oscillations, could provide a way to protect qubits from decoherence, making quantum computers more robust and reliable. Imagine a future where time crystals act as the backbone of quantum networks, enabling breakthroughs in cryptography, materials science, and even artificial intelligence. The possibilities are as vast as they are thrilling. As we marvel at the strange and wondrous nature of time crystals, another exotic form of matter comes into focus, one that's equally mysterious and potentially even more transformative. Strange matter, a hypothetical state of matter composed of quarks, could rewrite the rules of physics as we know it. But what exactly is strange matter, and how does it fit into the grand tapestry of the universe? That's a question we'll explore next, as we continue our journey through the cosmos' most mind-bending phenomena. For now, time crystals stand as a testament to the universe's endless creativity, reminding us that even the most fundamental laws of physics can be bent, or perhaps reimagined entirely. Now, let's venture into the realm of the truly extraordinary, a form of matter so bizarre, it could rewrite the rules of physics as we know it. This is strange matter, a hypothetical substance composed of strange quarks, one of the fundamental building blocks of the universe. Unlike the protons and neutrons that make up the atoms in your body, strange matter is thought to be made up of quarks that aren't bound into protons or neutrons, but instead exist in a free, densely packed state. It's a concept that challenges everything we thought we knew about the stability of matter and could hold the key to understanding some of the universe's most extreme environments. To grasp why strange matter is so revolutionary, we need to take a step back and look at the basics of particle physics. Protons and neutrons, the particles that form atomic nuclei, are made up of smaller particles called quarks. There are 6 types or flavors of quarks: up, down, charm, strange, top, and bottom. In ordinary matter, protons and neutrons are composed of up and down quarks. Strange matter, on the other hand, is theorized to contain a significant number of strange quarks, which are heavier and more exotic. Under certain extreme conditions, these strange quarks could form a stable, ultra-dense state of matter, one that's far denser than anything we've ever encountered. But why is strange matter so fascinating and so controversial? For one, it challenges the very notion of what makes matter stable. In our everyday experience, matter is stable when its protons and neutrons are tightly bound in atomic nuclei. Strange matter, however, suggests that under the right conditions, quarks could exist in a freer, more fluid state, potentially making it more stable than ordinary matter. This idea has led to some startling implications. If strange matter is more stable, could it convert ordinary matter into strange matter on contact? Some theories suggest that if a strange matter seed were introduced to Earth, it could trigger a chain reaction, transforming everything it touches. While this scenario is highly speculative, it's a reminder of just how profoundly strange matter could reshape our understanding of the cosmos. The most likely place to find strange matter, if it exists, is in the hearts of neutron stars. These incredibly dense stellar remnants, born from the explosions of massive stars, are already extreme environments where matter is compressed to unimaginable densities. Under such conditions, the boundaries between protons and neutrons might break down, creating a quark soup where strange quarks could dominate. If neutron stars do contain strange matter, it could explain some of their puzzling properties, such as their unusually high density and the mysterious signals they sometimes emit. Discovering strange matter in neutron stars wouldn't just solve astrophysical mysteries. It could also provide a new window into the fundamental forces that govern the universe. As we ponder the strange and wondrous possibilities of strange matter, another exotic state of matter comes into focus, one that exists at the opposite end of the temperature spectrum. Bose-Einstein Condensates, a bizarre form of matter that forms at temperatures just above absolute zero, reveal a world where quantum effects dominate and particles behave as a single, unified entity. How do these ultra-cold states of matter work, and what do they tell us about the quantum world? That's a story we'll explore next. For now, strange matter stands as a testament to the universe's endless capacity to surprise us, challenging our assumptions and inviting us to rethink what we thought we knew about the very fabric of reality. Now, let's shift our focus to one of the most extraordinary states of matter ever discovered, a place where the quantum world spills over into the macroscopic, creating a bizarre and beautiful phenomenon. This is the Bose-Einstein Condensate, a state of matter so strange that it defies our everyday experience. Imagine cooling a gas of atoms to temperatures just a hair above absolute zero, the coldest possible temperature in the universe. At this point, something remarkable happens. The atoms lose their individual identities and merge into a single quantum entity, behaving as though they're one giant particle. It's a state of matter that blurs the line between the microscopic and the macroscopic, revealing the hidden unity of the quantum world. The story of Bose-Einstein Condensates begins with the work of two visionary physicists, Satyendra Nath Bose and Albert Einstein. In the early 20th century, they predicted that at ultra-low temperatures, particles called Boson's particles with integer spin could collapse into the same quantum state, forming a single, coherent wave. This prediction remained theoretical for decades, until advances in laser, cooling, and trapping techniques finally allowed scientists to create these condensates in the lab. In 1995, researchers Eric Cornell and Carl Wieman achieved this groundbreaking feat, earning them a Nobel Prize and opening a new frontier in quantum physics. What makes Bose-Einstein condensates so fascinating is how they challenge our understanding of quantum mechanics. In the quantum world, particles are often described by wave functions, which define their probabilities of being in certain states. Normally, these wave functions are localized to individual particles, but in a Bose-Einstein condensate, the wave functions of all the particles overlap, creating a single, unified wave that extends across the entire condensate. This means that the particles no longer act independently. They are entangled in a way that makes the entire system behave as one. It's as if the condensate is a single quantum object, visible to the naked eye. This unique property has profound implications for our understanding of the universe. Bose-Einstein condensates allow scientists to study quantum phenomena on a macroscopic scale, providing insights into everything from superconductivity to the nature of dark matter. They've even been used to create atom lasers, devices that produce coherent beams of matter waves instead of light waves. These applications are just the beginning, as researchers continue to explore how Bose-Einstein condensates can deepen our understanding of the quantum world and its connection to the larger universe. As we marvel at the strange and wondrous properties of Bose-Einstein condensates, another phenomenon involving light comes into focus, one that's equally mesmerizing and steeped in mystery. Cherenkov radiation, often described as the sonic boom of light, occurs when particles travel faster than the speed of light in a medium, creating a striking blue glow. But how can something outpace light, and what does this phenomenon reveal about the nature of light itself? That's a story we'll explore next, as we continue our journey through the cosmos' most awe-inspiring phenomena. For now, Bose-Einstein condensates stand as a testament to the universe's ability to unite the microscopic and the macroscopic, reminding us that even in the coldest reaches of space, there's warmth in the form of discovery and wonder. Picture this, a ghostly blue light glowing in the depths of a nuclear reactor, shimmering like an otherworldly aurora. This isn't a scene from a sci-fi movie, it's Cherenkov radiation, one of the most visually stunning phenomena in physics. Named after the Soviet physicist Pavel Cherenkov, who first observed it in the 1930s, this eerie glow occurs when charged particles, like electrons, travel through a medium, such as water, faster than the speed of light in that medium. Yes, you heard that right, faster than light, but how is that possible, and what does it tell us about the nature of light, particles, and the universe itself? At first glance, the idea of something moving faster than light seems to defy Einstein's theory of relativity, which states that nothing can surpass the speed of light in a vacuum. But here's the catch. Cherenkov radiation happens when particles outpace light in a medium, not in empty space. In water, for example, light slows down to about 75% of its speed in a vacuum. If a charged particle, like an electron, is zipping through that water faster than this reduced speed, it creates a shock wave of light similar to the sonic boom produced by a jet breaking the sound barrier. This shock wave manifests as that striking blue glow, a visual reminder that the rules of physics can bend in surprising ways. Cherenkov radiation isn't just a cosmic curiosity. It has real-world applications that shape our understanding of both Earth and the cosmos. In nuclear reactors, for instance, the blue glow serves as a critical indicator of radioactive activity, helping scientists monitor reactor performance and safety. It's also used in particle physics experiments, where detectors filled with water or other transparent media can track high-energy particles by capturing their Cherenkov light. Even in astrophysics, this phenomenon plays a role. When high-energy cosmic particles enter Earth's atmosphere, they create Cherenkov radiation, which telescopes can detect to study the origins of cosmic rays and other high-energy phenomena. But what makes Cherenkov radiation truly fascinating is how it challenges our understanding of light and motion. It forces us to think beyond the simple notion that nothing can go faster than light, and instead consider how light behaves differently in various environments. This phenomenon is a testament to the complexity of the universe, where even the most fundamental rules can have surprising exceptions. It's a reminder that science isn't about rigid absolutes, but about exploring the nuances and exceptions that make the cosmos so endlessly intriguing. As we marvel at the ghostly beauty of Cherenkov radiation, another profound mystery comes into view, one that's less about light and more about life itself. The Fermi Paradox, named after physicist Enrico Fermi, asks a simple yet haunting question. If the universe is so vast and ancient, why haven't we encountered any signs of extraterrestrial civilizations? With billions of stars and planets in our galaxy alone, the odds seem stacked in favor of life existing elsewhere. Yet, the silence is deafening. What could explain this cosmic quiet, and what does it mean for our place in the universe? That's a question we'll explore as we wrap up our journey through the cosmos' most perplexing mysteries. For now, Cherenkov radiation stands as a glowing reminder that even in the most familiar corners of science, there's always something new to discover, and always more questions waiting to be asked. Now, let's turn our gaze from the cosmos' dazzling phenomena to one of its most profound mysteries, a question that has puzzled scientists, philosophers, and dreamers for decades. If the universe is so vast, so ancient, and so filled with stars and planets, where is everyone? This is the Fermi Paradox, a haunting contradiction between the high probability of extraterrestrial life and the stark absence of any evidence for it. Named after physicist Enrico Fermi, who famously posed the question, "Where is everybody?" during a casual conversation in 1950, this paradox challenges not just our understanding of life in the universe, but also our place within it. To grasp the weight of the Fermi paradox, let's start with the numbers. Our galaxy alone contains over 100 billion stars, many of which host planets in their habitable zones, regions where conditions might allow liquid water and potentially life as we know it. With billions of Earth-like planets likely scattered across the Milky Way and countless more in the observable universe, the odds seem overwhelmingly in favor of life arising elsewhere. And yet, despite decades of searching, we've found no definitive signs of intelligent civilizations. No signals, no artifacts, no visitors. The silence is deafening, and it raises a troubling question. Are we alone, or is there something we're missing? One of the most compelling explanations for this silence is the Great Filter hypothesis. This idea suggests that somewhere along the path from simple life to advanced civilizations, there's a barrier, a filter, that makes it extraordinarily difficult for intelligent life to survive long enough to make its presence known. The filter could lie in the past, perhaps in the emergence of life itself or the transition from single-celled to multicellular organisms. If so, this would mean that life is incredibly rare, and we're among the lucky few who made it through. But there's a darker possibility. The filter might lie ahead of us. If civilizations tend to self-destruct through war, environmental collapse, or other existential threats before they can colonize the stars, then our future could be far more precarious than we imagine. The Great Filter forces us to confront not just the mystery of extraterrestrial life, but also the fragility of our own existence. The implications of the Fermi Paradox extend far beyond the search for aliens. If we're truly alone, it underscores the preciousness of life and the responsibility we have to protect it. If we're not alone, but the filter lies ahead, it's a stark warning about the challenges we must overcome to survive as a species. Either way, the paradox invites us to reflect on our place in the universe and the choices we make as a civilization. Are we destined to fade into cosmic obscurity, or do we have the wisdom and resilience to reach the stars? As we ponder these profound questions, let's take a moment to reflect on the journey we've taken through these 32 stellar phenomena. From the Great Attractor's invisible pull to the enigmatic glow of Cherenkov radiation, each mystery has revealed the universe's boundless complexity and wonder. These phenomena aren't just puzzles to be solved, they're reminders of how much we have yet to learn and how much beauty and surprise the cosmos holds. They challenge us to keep exploring, to keep questioning, and to keep marveling at the infinite possibilities that lie beyond our understanding. The Fermi Paradox may leave us with more questions than answers, but perhaps that's the point. In the face of the unknown, curiosity is our greatest gift, and the universe, with all its mysteries, is our greatest teacher. As we come to the end of this cosmic journey, it's time to take a step back and marvel at the incredible tapestry of mysteries we've explored. From the invisible gravitational grip of the Great Attractor to the fleeting brilliance of fast radio bursts, and from the eerie emptiness of the Boötes Void to the explosive energy of Kilonovae, these 32 stellar phenomena have challenged our understanding of the universe in ways that are as humbling as they are exhilarating. Each one, a puzzle in its own right, has pushed the boundaries of conventional astronomy, forcing us to rethink the very laws that govern the cosmos. Together, they paint a picture of a universe that is far more complex, dynamic, and mysterious than we ever imagined. What's truly remarkable about these phenomena is how interconnected they are. The Great Attractor and dark flow hint at forces shaping the universe on the grandest scales, while gamma-ray bursts and neutron stars reveal the violent beauty of stellar life cycles. Gravitational waves and Hawking radiation offer glimpses into the quantum realm, and the Fermi Paradox reminds us of the profound questions that remain unanswered about life beyond Earth. Each discovery builds on the last, weaving a story of a universe that is constantly evolving, full of surprises, and always ready to challenge our assumptions. These mysteries aren't just isolated curiosities, they're pieces of a much larger puzzle, one that we're only beginning to piece together. But perhaps the most inspiring takeaway from all of this is the reminder that there's so much we still don't know. Every answer we uncover seems to lead to even more questions, and every discovery opens new doors to exploration. This is the essence of science, not just finding answers, but embracing the questions that drive us forward. It's a journey that requires curiosity, creativity, and a willingness to venture into the unknown. And as we continue to explore, we're not just learning about the universe, we're also learning about ourselves, our place in the cosmos, and the incredible potential of human ingenuity. As the astronomer Carl Sagan once said, "Somewhere, something incredible is waiting to be known." These words capture the spirit of discovery that fuels our quest to understand the universe. Each of these 32 phenomena is a testament to the boundless wonders that await us, and a reminder that the cosmos is a place of infinite possibilities. Whether it's the enigmatic glow of Cherenkov radiation or the haunting silence of the Fermi Paradox, each mystery invites us to look deeper, think bigger, and dream beyond the limits of what we know. So, what's next? The universe is full of secrets, and the next great discovery could be just around the corner. Whether you're a seasoned space enthusiast or someone just beginning to explore the wonders of the cosmos, there's always more to learn, more to question, and more to marvel at. We'd love to hear your thoughts. What mystery fascinates you the most? Share your favorite moments from this journey in the comments below, and don't forget to subscribe for more deep dives into the endless mysteries of space. Together, let's keep exploring, keep questioning, and keep reaching for the stars. The universe is waiting, and it's more incredible than we can even imagine.